Okay, Aspen Plus tutorial number 2. This tutorial will cover physical property modeling. And so the objectives here, you're going to utilize the physical property estimation. You're going to use some analysis tools. We're going to use some theoretical models, pumps, all of this stuff. And tutorial assumes you have basic understanding of distillation, pumps, phase equilibria. I mean, distillation, you should all have some sort of idea, maybe not distillation columns, you're going to get them, you're going to learn them during your mass transfer, but distillation process, basically, you're taking advantage of a change or a difference in the boiling point between two species to separate them. Phase equilibrium and basic thermodynamics, basically. And then you have a bunch of other, you're just trying to talk about the introduction. You can read this at your own time. Okay, so part 1, physical property basics. So in this section, we'll experiment with different physical property models and use some of the special property tools, including Aspen Plus. So let's start by, we're going to synthesize a process which will separate a stream containing 70 mole percent methanol and 30 mole percent chloroform into high purity pure methanol and high purity chloroform. So let me highlight this so it's easy for me to locate. At this point, we know nothing else, so let's use Aspen properties to get some useful information. So you're being told to make a new simulation and use metric units for convenience. So now I'm going to switch to Aspen Plus, and I'll be reading along the tutorial. So you could, if you're sort of following, I'm just reading from this section onwards. Okay, so this Aspen Plus, all I did was open a new blank simulation file, and this is what I get. And so you're being told that the first thing, use metric units for convenience. So again, if you recall, Aspen Plus, you have basically the two main tabs we're dealing with are the properties and the simulation. Should always start with your properties. This is where I'm going to set up or let Aspen know about my chemicals I'm using, about my thermodynamic package which I want to use, and then I move on to property where I start doing more of the chemical engineering stuff, such as dropping my units, mass balances, my mass streams, temperatures, pressures of operation, etc. And this is similar to what we talked about in process design. Start off by creating your database of all your chemicals, and then you start moving on to building your base case. Okay, so it's telling you to change it to metric units. And again, if you recall, we navigate using this left-hand side tree here. And under specifications, this is where I define my units. And instead of using this set of units, which is metric with bars for pressure, I'm just going to use metric. Okay. And then you're being asked that under the simulation tab, in the setup reports option stream tab, make sure to check the mole fraction basis box for later. So let's navigate to the simulation tab. And again, you navigate using this bottom, on the bottom left-hand side, you can navigate between the tabs. And you're being asked under simulation, setup, report options. Here, again, you also navigate using the left-hand side, stream, check the mole fraction basis. Okay, fraction basis mole. So I'm gonna check this mole fraction basis. Then I'm gonna go back to properties, navigate back to the properties tab from the bottom left corner here. Okay, so now under the properties tab, under components, I'm gonna specify two things, methanol and chloroform. Because they're common chemicals, you can just write them. So if I write methanol here, methanol, and I click on tab, it's gonna show up. And then the next chemical is chloroform, right? Let's wait for Aspen to wake up. Yeah, Aspen always lags on my laptop. If it lags on your machines as well, it's fine. Just be patient, or if it lags on the virtual machine. So if I wrote chloroform and Aspen couldn't recognize it, so the way in which you know that Aspen recognizes it is that it allocates a component name to your component ID. In this case, there is no component name, which means Aspen doesn't know what this is. So I'm going to delete this row, and then I'm going to search for chloroform. I'm using the search panel here, chloroform. And again, always be careful of the spelling. A common error from the past bunch of guys, past group of students, is that you do a small mistake here, and you have a very strange chemical in your process, right? Because if you look here, I just wrote chloroform and I get 50 different things. So just be careful with your spelling and what you're choosing. Okay, let's move quickly. So after specifying your components, the next step is always under your properties tab, you need to specify two things: your chemicals under component specifications, and then your methods under the methods here. So I'm going to expand the methods tree. I'm going to click on specifications, and you're being asked to use the non-random two liquid model, which is NRTL-RK. As you can see, NRTL-RK is not one of the common models. So if you can't find it using the common filter, you just need to go up to filter and all. This way it's going to show you all the models which are available in Aspen. And here I can navigate to NRTL-RK, and then everything should be fine. A common thing with Aspen is that under parameters, it might still show you this red arrow. Just navigate to where the error is, click on it, and for most versions of Aspen, it will retrieve it automatically. If it doesn't retrieve it for some reason, just go up here and click on Retrieve Parameters under Tools. Okay. So we did this. And you're also, in the tutorial, you're being asked to deal with this binary interaction error. And this is a common error. The thing you just need to keep an eye on it, because if you go to simulation, you keep on getting errors in your simulation. Sometimes it's because of this very simple thing. Okay. So this is done. And the next thing you're going to do is, there's a lot of talk, or basically a thermodynamic refresher for you guys about fugacity, activity coefficients, whatever. So the idea of an activity coefficient or idea of fugacity is, pressure. The basic idea of pressure is you have molecules bumping each other, or molecules bumping against a boundary, and this exerts a force, and pressure is basically force over area, and that's how you get pressure. However, what fugacity does, or what an activity coefficient does, is it accounts for the chemical nature of these molecules, right? Because all molecules have a chemical aspect to it, so you need to adjust for this chemical nature when trying to calculate this pressure from a molecular level. So that's the idea. And there's a refresher here that goes into Gibbs free energy, and thermodynamics, you can get very fancy if you want to, but for our cases, we just want to use it as a tool for Aspen. Okay. So you're being asked, just worry about the terms Aij through Fij, constants determined by regression. They were just fixed numbers, and Aspen properties is a nice database containing thousands of these constants. To load them, click on the red half circle in the binary interaction folder in the subheading NRTL1. So I'm now halfway through page 4, and you're being told to click on the red half circle in the binary interaction folder in the subreddit NRTL1, and this is what we did. And basically you can see all the parameters here. And question number 1, you're being asked, report the value of Cij contained in the Aspen plus NRTL-RK databank, where I is methanol and J is chloroform. So in our case, I is methanol, J is chloroform, and Cij Cij is 0.3. Okay, so you can retrieve these binary interaction parameters, which are used in your thermodynamic model when you're dealing with mixtures. And you just the idea is that you need to acknowledge that once you get pretty advanced with this Aspen simulation, you are capable of toggling all of these thermodynamic parameters, right? So if you end up being like working with compressors or working with some other piece of equipment that's fundamentally based on or operates based on an obvious thermodynamic principle or a complex thermodynamic principle, you might want to play around with these parameters. Okay. So this completes part 1, it seems. So let's move on to part 2. Okay, so part 2, you're being asked, Aspen has a lot of physical property data, You can get it by parsing the retrieve parameters. Yeah, so if you want, you can retrieve all your parameters by just clicking on retrieve parameters here under the tools. You can retrieve them. Yeah, I'll give you a warning, just okay. And it's gonna retrieve all your parameters. Of course, you can follow the pictures if you want. And then in order to see all the parameters which were retrieved, we're going to go down to the methods, parameters, results. I'm gonna go methods, parameters, which is already open. And then I'm going to go to results. And it gives you a prompt asking you to go there directly. So let's do that, it's fine. And you can see all the parameters available, all thermodynamic parameters available, all types of thermodynamic parameters. You know, it's just how it is. And they're coded. So basically you have critical pressure. This is molar density, you know, all types of parameters. And if you're not sure what a parameter represents, you can just copy this parameter name and put it in the help. So to get the help, you can just click on F1. Your help prompt is going to show up, and then you could find out what this represents. Okay, so and you're being asked to look in the T-dependent tab of this form. So I'm asking you to, after retrieving the parameter results, which you can see here, your results show up and you have 3 tabs. You have the scalar parameters, the T-dependent parameters. You're being asked to click on the T-dependent parameters and find out what the equation used in the vapor pressure is. Elements 1 through 7 are coefficients C1 to C7. Okay, so you're given an equation which is your Antoine equation basically, and it has 7 constants. And it's asking you to find out what is C2. So if I go to T-dependent, and so C2I for methane is 1. So this is the answer to Q2. Okay. No, actually you're being told to navigate to PLX end. So let's just be careful. So under T-dependent, you have another set of, another menu to select your parameters. We're going to select it. You go to PLX end, which is your Antoine equation parameters, and you want to find C2 for methane, for methane. Okay, so question 2, you're being asked to find C2 for methane. However, the problem is methanol, right? Let me just, yeah, the problem is methanol. So it could be one of two things. It could be either that question 2 has a typo, or you're being asked to find it for methane. Doesn't matter. If you want to find it for methane, all you have to do is go up here to components. Under specification, I'm just going to add methane to my list of chemicals, right? I add methane to my list of chemicals, and then I ask Aspen to retrieve all the parameters for methane. It will retrieve it, and then I can navigate and get this constant for methane. Right, so you can really use Aspen as a database to get any thermodynamic information you need about the chemicals you're dealing with. Okay, view the results. Okay, T dependent, and we want the vapor pressure, which is PLX A and T. Do it right here, and then we're looking for methane, C2I for methane, and you can see that C2I for methane is -1,324. Okay, so this is question number 2, or might be a typo, whatever it is. You just feel comfortable navigating. Give me either answer, it's fine. Okay, so part 2 is concerned with navigating and retrieving physical data, navigating this physical data. You know, if you're building your process, you can always use it to get, you know, critical points. If you can't find them online for some reason, always use Aspen to give you these parameters. You know, some parameters like critical volume, molar density, sometimes they're very hard to find online. You know, the compressibility factor. So Aspen will retrieve them for you very easily. Okay, moving on to part 3. So before moving on to part 3, I want to get rid of this methane. I just want to clean up my flow sheet here. So let me get rid of it. Let me save this process as well to avoid, you know, crashing on me or something. Let's call it tutorial number 2. There we go. Good. Okay. Part 3, creating a VLE diagram. So let me share my other screen just to show you where I am. Hopefully, still following. So part 3, I'm here creating a VLE diagram. And in this step, basically, I'm going to use Aspen to create my vapor-liquid equilibrium diagram. And there's a whole bunch of text here. You can always read it. But what we're going to do is we're going to follow these steps, okay? To see the VLE, it's usually most convenient to see a TXY diagram. So you need to go to the analysis section of the menu and then select binary. So this will be our starting point. You know, this is the thread which we're going to catch from here. So let me show you where this exists. So what you're being asked to do is go to the analysis section, which is right up here. You see analysis, and you're being told to select binary. And this should show up a dialog box, which you could use to do your manipulations. Okay, to see the VLE, it's usually most convenient to see a TXI diagram. So you're being asked to set the analysis type to TXY, and then choose the 2 components you want to compare. So I want a TXY diagram. I'm comparing methanol to chloroform. And this TXY diagram, you're gonna get sick of it. You're gonna see it every day in mass transfer. And it forms the basis of, you know, separation, all types of things, and this is how you get it. Okay, you then choose the 2 components you want to compare, methanol and chloroform. I only have 2 components here in this case. And you can also select the range of mole and mass fractions of the primary component that you want to look at. Usually you can just leave it as 0 and 1. However, sometimes you need to focus on a particular range. Okay. So what it's saying is basically TXY is the most common one. You select your species from here, and here you select the basis for the variation. So maybe you want to have this analysis over a range of mole fractions or a range of mass fractions. And you know, because it's a fraction, it ranges from 0 to 1. And then you just tell it how many points do you want to generate this plot. Okay, and you know, if you want to focus on a certain region, so if you have an azeotrope and you know they intersect, you want to look at the lower concentration end, you can change this to a lower concentration. And you can tell it at how many points. Saying here default is 41. You might see 41, but for me, I'm seeing 50. It doesn't matter. You can change it. You can make it 1,000 if you want to. It's up to you. Don't make it 1,000. Your computer is going to crash. Okay, and then you're being told that in the upper right hand of the form, you can pick which phases we are looking at. Okay, so where is this? Okay, so just be careful because if you look at the pictures in his book, it's for the older version of Aspen. So this is a newer version. So you're I would just I wouldn't worry about it. So you're just being asked, in the older version, you had an option to only look at the vapor part of the graph or look only at the liquid part of the graph. In this case, in this version, so I have version 10. I think on the servers there's version 11. And just the main parameters you need to set are methanol, chloroform, and the range over which you want to plot. Okay, anything else we need to worry about? Let's have a look at the other tables, other tabs here. So tabulate, what does this do? Let's just have a look. PS1, okay, what does this mean? So here you also have the option of selecting another parameter to plot for your system. So example, because I have an XY system, maybe I want to Aspen to also at the same time just calculate the heat capacity of this mixture, calculate the enthalpy of this mixture. So you can always use this utility to tabulate it at the same time. I'm gonna get rid of this guy. Okay, to delete them, I think we have to go back here and delete them from the tree. And this is very common with Aspen. Once you create one of these sub elements, we will need to delete it. And we're still in the analysis. So, if you get lost or you click somewhere and you don't find your analysis, you can always navigate to it from the tree here. So analysis, binary, input, this is where we were. And let's continue just having a look at the other tabs. Calculation options, what is this? Okay, here you go. So in this version of Aspen, your valid phases have been moved to calculation options. So let's just change it to vapor liquid. Doesn't really change anything because you only have two components. You can't have vapor liquid either way. And maximum iterations. So maximum iterations is something you need to keep an eye on because sometimes you have a problem which seems simple, but Aspen is having a hard time finding a solution. And you can control this by changing your maximum iterations. You can increase these iterations, I think, up to, for some calculations, up to 200, for others, up to 1,000. And you can use it to ask Aspen, just keep trying until you get an answer. Some people like to reduce this error tolerance. So Aspen is iterating basically in once iteration n and iteration n plus 1, the error between them reaches a certain tolerance, and it says this is a satisfactory solution. And you always want this error tolerance to be as low as possible. So if you're having a hard time reaching a solution and you decide, okay, I'm going to change this error tolerance to maybe 0.01, then you're going to get a solution, but you have to be aware that, it might not be accurate, might even be wrong. Okay, there's nothing else to change here. So let's go back to binary analysis and let's run our analysis and see what is going to give us. So the analysis is running, give it some time, let it run, let Aspen, do its thing. Okay, so we did this and now we see our, TXY plot for the system. This plot is at what pressure? This plot is at only one pressure of 1 atmosphere. In your tutorial, you're being asked to plot it at 3 pressures. So the way to do it is you know, this is only at 1 atmosphere. If I want to plot them at different pressures, so I can go here. Let's plot it at, so you're being asked in the tutorial to plot it at 1 bar or 1.01325, 5 bar, and 10 bars, okay? So if I do this and I run the analysis, I should see 3 TXY diagrams at the 3 different pressures now, okay? Give it some time, let it run. And as you can see here, we have 3 diagrams at the 3 different pressures. And you can always look here at the, you know, so the purple and green lines, sorry, the purple and, I don't know, they both look purple to me, but let's take another one. The green and gray lines here, they're both at 5 bars. I don't know, this color and this color, they're both at 10 bars, and they're both purple. I don't know. The 2 purple ones are 1 bar. Anyways, so you can plot at different pressures. This is how it is with Aspen, and you could use it to get these diagrams. You know, if you want to determine the best temperature at which you achieve a separation, you're gonna do this in mass transfer, but you know, later on in the course or maybe next semester, if you want to use or make a design decision, make a decision on the operating conditions, this is how you retrieve these plots. Okay. So you have a couple other questions here. You're being asked question 3. What's the boiling point of chloroform at 10 bars? Hopefully you remember how to do this, but you would need to read it off this diagram, right? Sorry, 1 second. Okay, let's get back to it. My computer froze for some reason. So we were at question number 3. What is the boiling point of chloroform at 10 bars? How do you get the boiling point here? You can definitely try and read it off this chart, you know. So the boiling point will be, so you're being asked at 10 bars. So where's the graph at 10 bars? It's this graph right here. So the boiling point of chloroform will be either this end or this end, right? So this is the mole fraction of methanol. So 1 methanol means 0 chloroform. 0 methanol means 1 chloroform. And the boiling point of chloroform will be this point. If you want to get the exact specific number, you probably want to look at the results in some sort of table format, right? Especially if looking at a figure like this. So in order to get all of these results in a table format, we need to find these results in a table somehow. So where do we find them? Let's try to look around. So if I go back to my binary input here, I have a results tab. If I click on this results tab, I will see all my results for all for both species, right? And if I'm looking for 10 bars, so I can navigate all the way to 10 bars here. So you're looking 10 bars, you're looking for chloroform. So mole fraction of methanol has to be 0. So let's go up, find the 10 bars 0 point, which is pure chloroform. I'm looking at this line, and the temperature is 426.4695 Kelvin, which corresponds to 153.545 Celsius. So this will be the boiling point of chloroform at 10 bars. And this point corresponds to this point on the diagram, which is, 426 or something. Let's go back and verify it. Sorry, I'm looking at not Fahrenheit, Kelvin. 426 Kelvin, right? Which is 153 Celsius. Okay. Question number 4. What is the liquid phase activity coefficient of methanol for a mixture of 70% methanol and 30% chloroform at 5 bars? Again, this information, you can't really get it from this diagram. So I need to go back to my binary analysis. And again, if you can't find this somehow, or if you can't find this, you can always navigate to it from the left-hand side tree, go to analysis, expand binary, click on input, and then I go to the results tab. And I'm looking for 70 methanol, 30 chloroform at 5 bars. Let's navigate to 5 bars. And I'm looking at this point here, which is 0.7 methanol, 0.3 chloroform. And you need to get the liquid phase activity coefficient of methanol. Activity coefficient, again, if you remember, this is the gamma. This is what it corresponds to. This is the activity coefficient. And the liquid phase activity coefficient of methanol, which is the liquid gamma of methanol, is 1.0569, right? So again, just read the table, try to locate it slowly, you'll find it. Okay, question number 5. At what mole fraction of methanol does the azeotrope occur at 5 bars? Okay. So at what point does the azeotrope occur at 5 bars? For me, it seems that this is something easier to read of the figure, right? So at 5 bars, the azeotrope occurs somewhere in this region. Okay, but here it seems that the figure is a bit messy in this region. So I can narrow it down. So I know it's somewhere between maybe 0.4, or maybe let's say 0.4 and 0.55 at 5 bars. So I'm gonna go back to my table here and I'm gonna read it off here. So we said it's somewhere between 0.4 and let's say 54. And I basically need to find the point. What point am I looking for? I'm looking for the point at which what? Right, azeotrope. What's the definition of an azeotrope again? It's the point when you have basically a change in boiling points between the two species. Let's go back and see if we find anything here which makes sense. So you can use this liquid mole fraction to help guide us, right? Because this will be the point where your liquid mole fractions are the same as well. So let's try to read it. 0.4 and 0.54, and the point where they're equal, it's not this one. We're looking at the vapor fractions here, and it seems to be somewhere around 0.47.52. Where does the cross happen? The cross seems to be happening somewhere here, right? No, around 0.52 mole fraction of methanol, right? So this seems to be where my azeotrope occurs. And again, I'm not looking at these liquid because this is what I'm plotting, this is what I'm changing basically, and this basically corresponds to this. These two are the same value. But I'm looking at the vapor mole fraction, and the azeotrope happens when they intersect. If you don't remember what an azeotrope is, just revise it. It's not like, I mean, it's somewhat common if you're dealing with hydrocarbons, but Anyways, so from reading them from the diagram, we're looking at the vapor mole fraction, finding the point where the vapor mole fractions intersect. And from here, it seems to be 0.52 methanol. Okay, let's move on. Taking so much time on this now. Okay. All right, so now I'm moving to part 4, and there are always parts here in the tutorial. You can read them at your own leisure. Okay, part 4, pressure swing distillation. And so what this part is telling you is, it is telling you to use these diagrams to guide your separation logic when designing these distillation columns. And what basically is telling you, so if you look at figure 5.2 in your tutorial, let me go back to the tutorial and share it. It's telling you, so if I perform a separation here, one separation, and then perform a second separation here, I will get a better overall separation, where I feed my product at 70% methanol, feed my mixture at 70% methanol, and I get one feed, which is very high purity methanol, and one feed, which is very high purity chloroform. And in order to do this, I would need to do two separations to take advantage of this basically intersection of boil, or yeah, intersection of your VLE diagrams. Okay, and the way to design it is we're going to have distillation column 1 here, pump distillation column 2 at the top. Again, if this does not make sense or you're having a hard time seeing it, just don't worry, just follow the tutorial now. Try to learn how to navigate Aspen, how to drop, how to use these different utilities. And then by the end of the semester, once you're finished your mass transfer, once you're finished your kinetics course, everything will start to come into place and the picture will start to make more sense, okay? So for now, let's just go to, let's go to Aspen Plus, and let's go to our simulation flowsheet and try to replicate this flow diagram right here, okay? So I'm gonna navigate back to Aspen Plus, and I'm gonna try to replicate this diagram with all these inputs right here, and this is basically what this tutorial is asking you to do. So let me navigate to this guy. Let's make sure we're sharing the right screen. Good. And I'm gonna start posting the Aspen simulation files as well on Blackboard. You know, if you're having a hard time opening them or there's some compatibility issue, then you might have these issues. But for now, I'll just post them for your reference. If you should be able to open them. The databases might have different names, might give you a warning sign or warning prompt, but should be fine. Okay, let's move on. Let's try to do this. So I went to my simulation tab. I'm gonna close out to this guy and see my main flow sheet. And what I'm doing is I'm basically replicating the flow sheet given in the tutorial. And in this flow sheet, you can see I have three things. We have a little pump in the middle, right? And again, remember that Aspen controls are sticky. So once I drop a pump, I still have this plus. I need to click on escape to get out of it. And then I am gonna add two distillation columns. So distillation columns are under columns, right? And we need to use two models. Which models did they ask you to use in the tutorial? Let's have a look here. Let me just have a closer look. So you're being asked to use radfrac, is it for both columns? Okay, so let's actually follow the tutorial. They don't want you to draw the entire thing. They want you to do it piecewise. Okay. So you're being asked to go to the flow sheet window and simulate the first column using a feed of stream A with the correct mole fractions. Okay. So let's use redfrac, and to do this, we're gonna do redfrac. So let's use the redfrac model. I'm gonna drop my installation column. I'm gonna rename it to column 1, and then I'm gonna add a material stream here. Again, to add a material stream, you need 2 clicks, 1 click to start, and then 1 click to connect it, and then you need to release this cross by clicking on escape, and then I need to connect the two outlets from the stream. I have my bottom here from this column. Sorry, I have my bottoms, and again material. 2 clicks, 1 click at the arrow, 1 click to release it, escape to release the mouse, and then a second click here. I'm gonna connect the top one. I might have to change it later based on the tutorial, and I get S3. And I'm gonna rename them as A, B, and C just to follow the tutorial. So let me rename this guy A. We'll rename this guy B, and we'll rename this guy C. Let me get rid of this strip at the top. Okay. So you're being asked to specify A. So in order to specify A, I'm going to navigate to it from the tree on the right, or you can double click on it, doesn't matter. Double click here, and you want it to be 70% methanol, 30% chloroform at 1 bar, right? So we said pressure is 1 bar. The overall flow rate is, temperature you're told is 30 Celsius. Overall flow rate is, I saw it here a second ago, is 200 kilomole per hour. And your mole fractions, and again, be careful, we need to change the mole fractions to select the right composition metric, right? So in this case, it's mole fraction, and I'm going to share the screen. Mole fraction, I want 0.7 methanol and 0.3 chloroform. Okay. You're being told to use redfrac for the column. So let's navigate to the column. To navigate, left-hand side here, tree, column 1, gonna click on it to open the column. The tutorial, you're being asked to use redfrac for the column with 35 stages. So I have 35 stages. Reflux and boil-up ratios of 3.2. So I want my reflux, my boil-up ratio, and my reflux ratio to be 3.2. And let's set the condenser to be a total condenser. Why is Aspen not happy here? Okay, so I think the reason Aspen is not happy is that we connected the stream to the top. So let me reconnect source, and I'm gonna connect it here. And then this should be okay with Aspen, hopefully. I'm gonna have it total, and this should be fine, okay? And selecting this or that in this column is, they both have different specifications. We'll get to it later on as we progress throughout the tutorials. Okay, we set both the boil up and the reflux to 3.2. Let me save my file. Feed stream A to stage 15. So let me feed stream A to stage 15. So it will be above stage 14, right? Set the pressure of the stop stage in the condenser to be, so I need to set the pressure, the top stage to be 1.01325 bars, and your feed stream will be at the same pressure. So I think we set the pressure of A, which is our feed stream, to to 1. Let's make it the same, 1.01325 bars as well. And let me go back to my column here. Just go back to specifications. And again, I'm navigating using the tree on the left-hand side. And this is where you should do, like, this is how you should navigate really. And I want to change this to bars. So just be careful exactly what you're doing and what you're selecting. Okay, then you're being asked, so now I'm on page, let me share the tutorial. So now I'm at this point, right? Page 11, here, run the simulation, you'll notice you get an error message. So let's do this, let's run the simulation and see if we get this error message. So how do you run the simulation? Again, you go to home, click on run right here, give it a few seconds for it to run. Okay, good, so it ran. And we're getting an error similar to what you're being told, right? A quick look at the control panel. So run control panel. And you can have a look here anyways at your results summary. So usually when you have an error in one of the units, you get the status with a link, which will take you directly to this unit. So this is what we're doing here. I'm gonna click here, it's gonna give me this. Artifact not converged in 25 outside loop iterations. Okay. So it seems that it's not converging for some reason. And 25 basically, after 25 iterations is still not converging. So how do we deal with this really? This is a common error you see with distillation columns. So one way to deal with this is to try and increase. So we need Aspen to run for more than 25 iterations. In order to change this, I need to navigate on the left-hand side under the column. And you should see something under the column here under conversions, right? You should see like a small file conversions. Click it, click on estimates, see if there's anything you can. So sometimes you can give Aspen some initial answers and Aspen can makes it easier to iterate. Otherwise, go to conversions and let me just set it to a much higher value. So let me set it to, will it take 1,000? Between 1 and 200. Okay, let's set it to 200 and see how it is. Let's rerun the simulation now with 200 and see if this error is going to go away. Okay, so once I set 200 and run it, it seems to be running fine. And so you have question number 6. What is the purity of methanol being produced? Should be close to what we predict from the diagram. Okay, so I need to find the purity of methanol produced. So in order to find this, I need to look at the compositions of these streams. And there are 2 ways to do it. I can either click on each stream and look at its composition. I can either find it from the results summary here from the streams, or I can look at the results of the unit itself under stream results, right? So there's a bunch of ways to see this answer. So I just navigated to the overall stream results here. And I need to find them. Is it the mole fraction or the mass fraction? Mole fraction of the methanol produced. Mole fraction, as you can see, the mole fraction of the methanol produced is very high. It's 0.99. Okay, very nice. And this is stream number B. So basically, B which is the liquid stream, will have most of your methanol. C, which is the upper stream, will have most of your chlorophyll. Okay, there's also another question here. What is the temperature of the azeotrope in degrees Celsius? So what's the temperature of this azeotrope? Do you have any temperature information here? We don't have a temperature, but what do they mean by the azeotrope? They're talking about this top stream. So what I'm doing here, because the two, so if you recall in your tutorial, we said we're going to do a two-step separation. First step, I'm going to remove almost pure methanol. And then my mixture here at the top is at its azeotropic conditions. And then I'm going to take this azeotrope, pump it up to the other side of the thermodynamic curve, and then do another separation, right? So the temperature of this azeotrope, which is, or the temperature of stream C, is, let's have a look here. I think it was 326 something, if I remember when we were looking, so it should be about 50, right? So 326, and it's given in Kelvin here. You can always change the units by clicking, and the temperature here is 53. So to answer question number 6, the composition of methanol is 0.99. The temperature of the azeotrope, which is what's leaving from the top, is 53.6. Okay. So now we're done with the first column. Let's add the second column. I'm gonna go back to the main flow sheet. I'm gonna close out of these tabs. I don't like these tabs to start accumulating, because sometimes they accumulate and then becomes hard to navigate. Okay, so I'm going to drop a second red-frac column. Again, remember the sticky controls of Aspen. Click on Escape to release your mouse. And I think we'll have to add a pump between them. So I'm just going to move these guys around, give myself some space. And again, you can select the whole thing and just drag it. Then I will drag this guy here. So let's add the second column. Let's also use 35 stages, reflux ratio 3.2, and a boil-up ratio of 7. So here I have 35 stages. Let's make it total reflux ratio of 3.2 and a boil-up ratio of 7. Condenser pressure should be 10 bars. So let's go to pressure here. And I want my condenser pressure to be 10 bar. Sounds good. Based on figure 2.6, let's guess 10 bar for the feed stage. That's what we have here. And then for our feed, can we put the pressure for the feed stage? Maybe not at this stage. So at this point, we need to add a pump to pump it to 10 bars. So let's add a pump here. And the pump will be in, where is it? Maybe manipulators. Pressure changers, sorry. So I'm gonna add the pump here. And I added the pump and now I need to reconnect it. So I'm gonna right click on C, click on reconnect destination, connect it here to the inlet. And then I'm going to select a new material stream, connect it from the outlet of the pump to the feed of this column. Okay. Now let's click on this thing, and so where do we add the feed? Does this give us any information, or we can guess actually? Doesn't matter. Let's just use the same specification we used for the last one, which I think told us stage 15. So I'm gonna say above stage 14 and fix it here. And one thing we need to remember, so we specified everything for this column, right? Okay, there's something not right here. Let me rename these so it's easier for me to navigate. So I'm gonna recall this pump. I will call this stream, what is it called in the tutorial? Just going to navigate up. I'll call this stream, let's call it C pump, or maybe this becomes confusing. C1, so it enters the pump as C, leaves at C1. Then I have two streams here. Let me call this E. So let me rename this guy as E, and then I'll connect the final stream at the bottom. And this will be D, okay? So now let's navigate to these guys and see what's going on. So why is it not happy? So column 1 is fine. Let me actually rename the second column as well. B3. I don't like this name B3. I'm gonna call it column 2. Okay, and let's navigate on the right hand side here. So I don't want the streams. I'm looking at column 2. So column 2 is fine. I think it was just missing the connections. We did the connections. So now let's go to pump and fill out the information here. And we're pumping this liquid to 10 bars, right? So I want the discharge pressure to be 10 bar, okay? And one thing the tutorial guy tells you is that even though in our diagram you're being asked to recycle, however, you should never add a recycle until your simulation converges without a recycle. Okay, and this is very important to remember. If I add a recycle at this point, it will never solve. Aspen will struggle immensely. I need to run it like this, have the answers. Once I have the answers, then I'm going to add a recycle stream. And this should always be the logic, because Aspen, it's not a magical tool. It's just trying to solve a system of equations, right? So you want to at least give it an initial guess before solving the next problem. So we have everything connected. Let's run it now. So I'm going to go home, then I'm going to run. And we'll wait for it to run. If we get any errors, we'll deal with them. We maybe change the conversions of the second column, do something about it, maybe increase the number of stages, whatever it is, or we can always deal with this. So again, we have an error in column number 2. Let's have a look here, see what's going on. Red frac not converged. So again, I need to increase the number of iterations. In order to do this, in the tree here under column 2, I'm going to go to conversions. I'm going to click on conversions, and I'm going to increase this from 25 to 200. Okay. And let's run it again, see if this solves the problem. Hopefully it does. Okay, so still not happy for some reason. So it's fine. So sometimes Aspen will struggle a lot in finding a solution. So in order to solve this type of problem, we need to give it an intermediate guess, right? So, maybe asking Aspen to solve 35 stages was too much. Let me change it to 10, and I'm going to change the speed to halfway through 10. Okay, let me make it above stage 4. And let's try to solve it with 10 first, and then I can increase the number of stages. Let's see if this works. And again, this type of, push and pull with Aspen is normal when running simulations, because, it's solving a system of equations, iterating all the stuff, and you need to give it an initial guess, all the stuff. So it's able to converge with 10. Let me increase it to 20. See if it can just use the results it got from 10 stages to get a result for 20 stages. And again, I'll use, instead of 4, I'll put 10 here. See if it will be able to resolve this. Let's run it. Okay, it ran fine with 20 stages as well. So now I'm going to increase or jump to 30 stages so it can use the solutions from 20 stages to try and predict 30 stages. And now I'm just going to put it at 14 or 15, and let's run it. And now it's converging at 30. Now let's move it to 35 and run it and get our final solution. Okay, so even though initially when we set it to 35, Aspen had a very hard time finding an answer. However, once I, stepwise get there, you'll be able to reach the point you want in your design. Okay, so I have two questions here. Question number 8. What is the purity of chloroform produced from a second column? It should be close to what we predicted from the diagram. Okay, so I need the purity of chloroform from a second column, which is basically E. So I'm going to look at overall results here. There's streams. It will actually not be E. It will be the bottom one because we pumped it across the azeotrope. So now the two products flipped. So it should have been D actually. So I'm looking at column D in this case. And what's the purity of chloroform? I'm going to navigate down to mole fractions here. And it's 0.94 chloroform. Okay, what's the temperature of the azeotrope? And again, the azeotrope will be the top from this column. And the temperature of the azeotrope is 403 Kelvin, which is 130.561 Celsius. Okay. So after we, mole fraction of the azeotrope is what we expected. So if you recall from the first part, we said that the azeotrope occurs at about 0.52. Here we're getting about 0.55, so it's fine, reasonable enough. So now I'm going to connect the recycle stream to the first column. Okay. So I'm going to add, so what I'm going to do is I'm going to recycle this stream back to the first column as a second feed. So in order to do this, I'm going to right click on E. I'm going to reconnect destination, and I'm going to make sure when connecting the destination, your mouse touches the blue arrow, right? You need to see this small yellow box. If you don't see it, you need to see this blue arrow, highlighted to a yellow one. Otherwise, you'll have an arrow which is very close but not connected. Okay, so just be careful, and then you can always move them. So I can always click on this blue arrow here and move it to the top, and you can see now that I have a recycle stream. One thing to remember is whenever you connect the stream to a distillation column, you need to specify at what stage is it being introduced, because distillation column is a big unit, has many stages to do that. So once I connected this recycle stream, you can notice on the left-hand side that column 1 turned from a blue check to a red circle. So let me go here to specifications, and it's because we didn't specify the input of the recycled stream. So E, which is the recycle, so you're being asked to try stage 8. So let's on stage. So I'm going to change it to on stage. And I'm going to put 8 here. Good. And now let's run it with the recycle. Let's see if we get maybe a higher purity of chloroform, or we get junk answers. Maybe it doesn't converge. Who knows? See how it works. Okay, so it seemed to work fine. Everything's good. We're able to run our closed loop simulation. It's looking good. And then you have two questions here. Question 10, what is the new purity of the chloroform? Okay, so I'm looking at the purity of the chloroform coming from stream D. So let me look at my stream results here. If you recall, before the recycled chloroform was at 0.94, right? Let's have a look here once it loads. Okay, mole fraction. So now the chloroform is still at 0.94. So, you know, nothing, it didn't really increase the purity of this chloroform. Wait, these results don't seem right. One sec. Did it update the results? Let me make sure it actually ran. Okay, so it ran fine. It just seems that this recycle does not, it wouldn't necessarily, it didn't change the purity. So this recycle or this second, you know, adding this recycle stream didn't really affect my chloroform purity, right? So it's still at 0.94. And question number 11, what's the new purity of the methanol produced? So methanol is stream B, right? I'm looking at mole fractions actually. So methanol now is at 0.92. Okay, so my methanol purity actually drops a bit and my chloroform purity doesn't change. So we can always increase these values. So, you know, once you get comfortable with distillation columns, you can increase the number of stages, increase the boil-up ratio, increase the reflux ratio, whatever, and we can get these as close as possible to 1. But, you know, the logic here now, so what we did in this tutorial, or what you should learn from this tutorial, is how to drop a distillation column, what are the parameters of the distillation column, conversions, how to increase the number of iterations, all of these things when dealing with the simulation. Okay. So then there's this final activity here. So now I'm on page 13. You're being asked, now let's learn more things about the system. The physical property system lets us find out considerably more information about the stream than what is in the stream results. So, you know, here you're only seeing, you know, a few parameters. You can get a lot more parameters if you want. And in order to do this, you should navigate to your stream, whichever stream you want. So let's say I'm interested in stream number D, for example, right? So I'm going to go to home. I have here stream analysis, but in order to activate this, let me navigate to a stream. Let's say looking at stream number B. And then I'm going to click on stream analysis here. So once you select the stream, zoom things. Stream analysis thing activates. I'm going to click on it. And then I'm going to click on bubble and dew point. And it will show you a lot of results, you know, a lot more results than what you'd usually get. Okay. Click on go to give me the bubble and dew point for this stream, and I can get a lot of information. So you can get a lot of extra information about the stream, which might not be obvious just from your typical chemical engineering master flow stream properties. Okay, what's the bubble point temperature in degrees Celsius of the chloroform product stream at 5.5 bars? Okay, thank you. So you want to find the bubble point temperature at 5.5 bars. I'm going to change this pressure to bar. Aspen just sleep today. There we go. Okay, we're looking at 5.5. So let me find the temperature. Sorry, find the pressure, 5.5. So at 5.5, right here, the bubble point of the chloroform product stream. So I want it in Celsius, right? It's 113. So this is actually for the B is the methanol, right? So chloroform will be the D stream. So I have to repeat the same thing for chloroform to get the bubble point of the chloroform stream. Okay, sounds good. And then what's the thermal conductivity of the chloroform product stream? Okay, so let's navigate to the chloroform product stream. Close out all of this. So our chloroform product stream, I think it was, let me just remember from, so it's D. Let's go to D. Stream analysis. So we can do the bubble and dew point, get the first thing, and then to get the bubble point, you just do this, and then you go to 5.5 bar. You're going to get it. And then in order to get the other parameters, so in question 13, you're being asked to get the thermal conductivity. So do this, go to stream analysis, go to point. And we're looking at what? Is this, what do we want? Thermal conductivity. Okay, thermal conductivity is more of a transport property than a thermodynamic property, but it's fine, you just select both and it will show you all the information you want. And we're looking for thermal conductivity, which is KMX, and KMX for the stream is 0.081. Okay, kilocalorie meter hours is a very, so in these calorific units, but if you want them in joule second meter, just change your units from here and you get 0.09. Okay, and then you're being asked to molar density, just look for the molar density from here, you're going to find it. Okay, this is the end of tutorial number 2. If you're having any questions, you're struggling, come to office hours. We'll go through it slowly together. We'll sort it all out. Thank you very much.